Let me now begin by studying discrete one-dimensional systems. An important point to make at the outset is that the dynamics of discrete and the corresponding continuum systems are very different. And let's illustrate this with two simple examples. The first example is just one of the simplest dynamical systems, that of exponential growth. So in the continuum, let's consider the one-dimensional system x dot equals x. And the solution to this is simple. X of t grows exponentially in time. But now let's take this continuous system and construct from it the corresponding discrete system. And the way we can do that is we first write the derivative explicitly as a difference. So on the left-hand side, x dot we can write as x of t plus delta t minus x of t divided by delta t, and this is equal to x. Now normally what we do is take the limit as dt going to 0. But to discretize the system, let's imagine that dt is a finite time difference, and let's choose that dt equals 1, and therefore the time is going to be a discrete variable that changes by 1 each time dt increases by 1. So the corresponding discrete system will be xn plus 1, so I'm writing dt as 1, and the time is equal to n, and so the dt in the denominator in the equation above goes away. And this is equal to just 2xn. And the solution to this equation is also straightforward. Xn is equal to x0 times 2 to the n. So in both cases, we have exponential growth, but with a different exponential factor. So in the case of a linear system, the qualitative behavior is the same, but the quantitative behavior is somewhat different. But now let's look at a more interesting example, which is a nonlinear system. And so in the continuum, let's consider the following equation. X dot is equal to x squared. And the solution to this equation is x of t is equal to x of 0 divided by 1 minus x of 0 t. So this equation gives rise to a divergence at a finite time. At a critical time, tc is equal to 1 over x0. But now let's do the same procedure as before and convert this continuum equation into a corresponding discrete equation. So the corresponding discrete equation would be x of t plus delta t minus x of t divided by dt is equal to x squared. And again, we'll write dt is equal to 1 and convert this into a difference equation. And what we get is that xn plus 1 is equal to xn squared plus xn. What you can check after the fact, but let me just state it without proof now, is that asymptotically the behavior of this equation is the same as if I ignore the linear terms. So I'm going to write this approximately as xn squared. And now this equation is very easy to analyze by just taking the logarithm. We have logarithm of xn plus 1 is equal to 2 logarithm of xn. And so the solution would be logarithm of xn is equal to logarithm of x0 times 2 to the power n, or xn itself is proportional e to the log x naught times 2 to the n. And the important point here is that there is no divergence. And you can check that if I include the linear term in the equation, that it doesn't affect the asymptotic behavior of the equation. So in the case of a nonlinear dynamical system, continuum and discrete behaviors are very different in the long time limit. And this is part of the reason that looking at discrete one-dimensional systems is actually very rich, because they are nothing like one-dimensional continuum systems.